So, I guess you can hear me now, at least sounds from here. I can't say because, yeah, this is no delay and this is very good technology. Yes? Oh, perfect. That's great. That's great. That's what I need. So we have around 55 minutes, so I will try to keep 10-15 minutes at the end for the questions. And we can go into deeper if you want. And before I begin, I want to learn a couple of things about who are here today. So can you please raise your hands if you're working in software engineering area in one way or another? Okay, almost everyone. Please raise your hand if you worked for less than 5 years. Okay, then if you work for 5 to 10 years. Great, and more than 10 years? Okay, good. Yes, but you probably won't learn anything new. So, today I'm going to talk about my personal road to 5 nines, how to achieve the high availability of the software system. And my name is Ilya Kaznacheev. I work as a cloud-native product architect at Capgemini. I previously worked at many different companies, from tiny startups to big enterprises like Deutsche Telekom. I worked in a public cloud provider. I worked in consultancies, and I'm also a Google developer expert on cloud. And last 13 years, I'm working with technology, and I'm pretty happy about it. And I need to turn on the focus mode, so there is no disruptions. So, 4 nines, what is it about, and what will you learn? The outcome of this session will be that you will know how to achieve the higher availability of the system, what components are there, and what, if you want to do that, if you want to drive your product, your company, your system to higher availability, what steps to do, and what are the main components of the thing, and actually, do you really need that or not? And I'm not trying to sell you the cloud, but maybe eventually I will sell you the cloud, because it will be about the cloud a little bit, but you can do that also without cloud providers, so just for you to keep in mind. And yeah, let us begin. So the first question is, how do we actually hit 4 nines of availability? Speaking of 4 nines, what it actually means? It means that our product is available via network 99.99% of all time. That means in a year, the downtime is less than an hour, which is, well, that's pretty difficult to achieve. And that's very bold statement if you make it. So how we actually do that? And the low-hanging answer may be microservices. Because, everyone likes microservices. We still don't know how to build them, but we all like them. But microservices, really, that I've seen maybe more bad microservice architectures than good ones, more that create issues than solve ones. It's not because microservices are bad, it's because people often try to apply patterns without those patterns to solve a real problem, and then they have problems. So instead of microservices, what we really need is redundancy. Redundancy is one of key pillars of the higher availability. And what redundancy means, that we need to, on every component of our system, we need to eliminate the single point of failure. The services, the databases, the network, load balancers, everything we have, every component we have, including third-party APIs, we have to eliminate single point of failure. And this is kind of what I can end the presentation here. This is the main point of higher availability, but not the only one, unfortunately. So how it works? If we add more replicas of something, it increases availability. Basically, we need to have at least 2 replicas of every component. We can have more, but more serve for load distribution, not for availability, but we need to have at least 2 replicas of basically everything. Not talking right now about systems with consensus, where we need at least 3, but like regular applications. When we add more dependencies in the chain, it lowers the availability. So say you service your application, your backend microservice talks to a second microservice, and they have like both 4 nines of availability. Say the full availability of the system is the multiplication of each one. And since each one is lower than 100%, then the resultant will be even lower than the different, not combined. And so I want to start with software architecture, since this is the DevFest. So many are probably developers. Let's start from what we know. How can we achieve the higher availability on software level? First, with the proper application design. What it is? First, applications should be stateless. That means all the state, all the sessions, etc., even cache should be stored somewhere, not within the application. Why? Because the application should be ready to be restarted, to be scaled horizontally, etc., etc. And yeah, as I said, it should be horizontally scalable. And it's not always important that it actually will scale, because not every component will have such a load that it scales. But you have to keep horizontal scalability in mind when you design the application. So everything you do within the application, you should keep in mind that there will be a second replica. So how this will be distributed between replicas. So for example, if you keep some information in the memory of your application, think, will this be available for the second replica when the load balancer will distribute requests there? That's very important architectural decision. Graceful shutdown. Since usually applications in highly available systems run in kinda cloud-native environment, they should be ready to be terminated, and they should end their service gracefully in less than 30 seconds. That means close all connections, save all the data in database, in Kafka, etc., etc. And applications should have health checks. So they have the way to tell the infrastructure if they're okay, if they're still running, if they're ready to accept new connections, or they should be already restarted. Then, of course, as I said, the services must be redundant. Why? Because, say we have 3 replicas, 1 replica goes down, we still have 2 to serve the load. And speaking of load, say the load is distributed evenly across 3 replicas. When 1 replica goes down, the load of this replica, X amount of requests per second, should be redistributed to the rest without overloading them. That means you have to keep CPU under a certain limit for each replica, and scale horizontally your system if load is higher. So you never have to keep load of replica up to 100%, because when 1 replica goes down, it will ruin the whole system. And we are starting talking about second pillar of the high availability is load management. How we distribute the load across the system. It's both about network load, about the data, about computation. And we start with load balancing. Also the vital component of the highly available system. So we see that we have multiple replicas and the load comes from somewhere. How it gets to the replica exactly? We have a load balancer before, which actually distributes the load. The simplest way is the round robin. It just gives to each component in the queue. But there may be more sophisticated mechanisms, more sophisticated algorithms, how actually to align the distribution pattern to the load on the current, on the each replica. And what load balancer does also, it does the health monitoring. So it actually sees is replica is alive. As we said, it should expose health checks. And if replica is not alive, it won't set send the request to the replica because they will be lost. And the other way around, if we introduce new replica, the load balancer will see this replica and start distributing the load to a new replica as well. And of course, we need to have the proper connectivity mechanism. So if we use synchronous communication, REST, gRPC, whatever, we should also build this properly so they are retriable, they are idempotent, and we make those communications pretty robust. We know how to resend requests, but we're also trying to not overload the system. If we use asynchronous communication, it's also important that the underlying brokers, for example, Kafka, also not a single point of failure. And they have multiple brokers, and those brokers are also set up the proper way that if we lose one broker, the communication still continues, and so on. And also in backend systems, such patterns as CQRS, for example, helps to establish good, robust communications. Also, event-driven communication is pretty robust. So it's not always about request response. It's often about sharing events, sharing states, and separating reads and writes in CQRS way. Then we have the second layer, is the data architecture, which is a little bit more tricky. Managing data is always tricky. So I'm not talking about data pipelines. I'm not talking about data analytics systems because usually those systems never have such high availability requirements. They are usually even eventually consistent. Yeah, of course, you may lose some data if your ingestion gateway doesn't work, but it's not that important that you get your response immediately. So I'm talking about classic backend applications, backend architectures. And here again, we have data replication. So the data should be in several instances so that if we lose one, and it's very realistic to lose some portion of your data, you will have the second one and you will have the automated way how to restore it. And the first is database replication. The standard scenario when we have some kind of SQL database, we have master replica and we have master and we have replica and we do replication. And the application connects to both, has connections to both of the databases. If we lose the master, it automatically starts to work with replica, and replica promotes itself to master and starts also doing writes. And this is very important because otherwise, if you lose the database, your whole ecosystem will go down, and that may be, not what you want. This is maybe a little bit different with document-oriented databases, which usually, like Mongo, for example, can work in master-master for different partitions, but their idea is the same, that your data is split between multiple instances of the database, which then in turn can be put into different physical locations. I will talk about this later. So if your data center will burn, you won't lose everything, at least on paper. Next is the very interesting pattern that I really like is decoupling via replication. So say you have two services, service A, service B, and your service A receives a request and sends some requests to service B, for example, to get some meta information from there. And the problem is if your service B goes down, you can't receive the information anymore, and so you cannot serve the request. And you have microservice architecture, for example, everything is isolated, but you have this chain failure, cascade failure, which is not what we want to achieve in distributed system. We want to achieve the opposite. How to do that? We can introduce a local storage. By local, I mean like the database belonging to this service A. And then we replicate some data that we need, not from the database, but from the service API or some events that we subscribe to. And we store this data locally. Again, not everything, but only kind of the projection that we need. So for example, if service B is the order service, and we want, the address to deliver the order, we can only store like the order ID and the address. And if they will change, we will replicate this change one way or another. But if we don't need that, we will just have this copy. And when service B goes down, of course, we cannot read and we cannot replicate the data anymore, but we still can serve the request because we have this local data. So we're no longer coupled with the availability of service B. And this service can work in isolation. Then the object store. If you run your own object store like Minio or something, of course, it should be replicated, the instances by themselves. But if you use cloud like S3, that's, of course, already replicated, and you can just rely on it. Next one, the platform architecture. So we're going kind of deeper and deeper and deeper through the technical stack, technical landscape of what we run. And how can I disable this notification? Sorry for that. So, going back to presentation. So, what about platform? When we're talking about platform, I talk first of all about Kubernetes or something like that, but it can be any platform, just virtual machines or Lambdas or something. I myself worked in a cloud provider when my team built Kubernetes as a service, so I know a lot about this stuff, but again, there are universal principles. And one of them is the fault tolerance, the next pillar of the higher availability. So your system should be fault tolerant. What it means that when, I'm not talking if, I'm saying when some part of your system crashes, it can repair itself, it can restart, it can retrieve the data and kind of return back to homeostasis as it was before. And the first part of this is the payload distribution. And talking about Kubernetes, it works this way, that the Kubernetes is a cluster of worker nodes, and each node has some applications hosted. Say we have green in 2 replicas, we have blue in 2 replicas, and we have magenta in 2 replicas. What will happen if node 2 will just die? Kubernetes will restart those applications in alive replicas. And it's done by the platform for us. We don't really have to care. The only thing we have to care is that our applications adopt this pattern, that they are stateless, that there are support horizontal scaling, and that there are support graceful shutdown. Then network. We have load balancers, and load balancer, of course, should be also not a single point of failure. So it must be at least several. And if you will take a look on the bigger companies like Facebook, for example, or Cloudflare, they have like an enormous number of load balancers distributing the load to enormous number of the backend machines. But if you will take a look, for example, on the Kubernetes, how Kubernetes networking is organized, each node has its own load balancer, which lands the request, which then redirects the request to the node where the service is running. And then it's redirected into the container. So if one node goes down, all other nodes still have those load balancers and routing tables, so they can redirect your request to the place where it should be processed. And then we have self-healing, another pillar of the higher availability. So what it is? First, the system, I'm not talking about singular application anymore. I'm talking about the whole system. And usually you build kind of on top of your application. So you have to have some kind of self-healing layer, which usually lives somewhere within the platform. It should autonomously detect if something is wrong. Usually it is done by analyzing the metrics exposed by applications. It should understand what actually happened. Maybe not the root cause, but like what is the kind of the issue and what to do with that. And it should be able to recover. For example, in many cloud maybe in all big cloud providers, if you have Kubernetes cluster, the nodes of this cluster are self-healed. That means if one node will die by any reason, the cloud provider will create another node, will set it up properly, and the load will be redistributed to a new node. The same goes for Cluster API, for example, the open source solution for managing Kubernetes clusters. Then replication, scaling, and balancing. The system should know how to replicate itself, how to scale horizontally or vertically, and how to balance the payload and how to balance the computation. Again, with Kubernetes example, this is the core capabilities of the Kubernetes, but the underlying infrastructure, like the virtual machines where Kubernetes nodes are running, should be able to do this as well, which again is done in public cloud providers, but can be done in just your local environment if you want. And it should have predictive maintenance where you know each time, you know through which steps to go. Your staff knows how to support the system, how to maintain the system, and there are no surprises. And if you have your own, like DevOps engineers, for example, SRE, they need to have They need to have trainings on how to support your system, how to maintain your system. So if something goes wrong, that should actually be able to quickly localize and locate and fix the issue. And then we have an infrastructure architecture. I will be talking a little bit less about it. It's about 4 pillars again. Compute, storage, and there should be network, but it's gone. Compute, storage, network, and IAM. So basically, it's usually a virtualization layer between your physical machines or the physical machines you rent from cloud provider, from hoster, and your platform. And those are also, should be not a single point of failure. An example with virtual machines or compute, that in many cloud providers and also in VMware, for example, there is a hot swap, I guess, feature when the memory of the virtual machine, the RAM, constantly being copied to somewhere else. And if your machine crashes, it will be immediately restarted from the more or less the same place on another virtual machine and will continue working, which is also very important thing if you want to achieve like very, very fast recovery, because otherwise it may take like 30 minutes to start another virtual machine with the applications on it, especially like the database. And if your applications are not ready to handle this kind of delay, you may again ruin the whole system. And in some cases, this is not what you want. In some cases, you can be okay with that, really, but not in every case. And then we have maybe the lowest layer of this is data center architecture, which again, servers and racks, which may look something like that. And I don't know, maybe you were or were not in the data center, but the modern data center is a pinnacle of engineering. This is very beautiful technical engineering system, which still has its own flaws. For example, the singular racks with multiple servers in it tend to burn together. That's why, for example, multiple cluster systems like Kubernetes, like Kafka, for example, have settings to set up different racks on which servers are running. So the cluster or the broker will try to put replicas of the same payload on different racks. So if you will lose one rack, if there will be an outage or fire, you won't lose all of your data the same way. It makes sense, right? And this is how all of those layers are interconnected. So you have to understand like what is below, what is on top of the layer you work with, the software layer, for example, to actually understand like what you should take care of. For example, on the platform layer, when you set up Kafka, you have to know where actually, on which racks in the data center your Kafka brokers are running to prevent losing everything. Like in a joke, like our server is down, but the good thing, we had backups, but the bad thing, backups are on the same server. So try to avoid this. Next, switches and routers. Again, not this switch, but more like this one. So yeah, they also should be, and they usually are duplicated. So data centers are designed with a very, very high level of redundancy. It's, I don't know if always, but I think always there are also two internet cables at least two different internet cables connected to the data centers of two different providers. Because you may have very different kind of outages, starting from the very mad excavator digging up your cable to just a provider going down or being canceled or something. And you have the data storage systems, which again, very, very interesting technology, which also replicates your data into different servers, different disks, which are then built together in arrays and store your data. This is more important for data storage. This is more important for data recovery. And there are some very, very interesting, complicated solutions to manage the data, like Ceph, for example. But keep in mind that the data storage is also so difficult, and sometimes if you work with data-heavy things, you may need to skip some abstraction levels. So you may want to work closer to the hardware. And the one layer on top, global availability. So it's not just enough for high availability to make your service, work good within the data center, be reliable, horizontally scalable, etc. Because as we know, the whole data center can just burn down. And we want somehow to prevent this, which called disaster tolerance, the ability of the system to survive disasters, such as losing one data center, which may happen because of many, natural reasons, like earthquake, fire, war, flood, etc. And the first is multi-zone. So in many cloud providers, what they give you is a set of data centers connected with a low latency network combined in one region, as they call it. This is called multi-zone or multi-AZ, availability zone in Azure, for example, and in AWS, I guess, as well, where your infrastructure already works in the way that it is spread across those data centers, usually at least 3 data centers, because many of clusters should have leader election, and they need at least 3 components to do so, like Kafka, like Kubernetes, like some databases, etc. So when you lose one data center, say in the region, what will happen? Kubernetes cluster, which is again spread across 3 data centers, will lose some nodes, but it will redistribute the data to the load to the different nodes. The data in databases, again, you may lose the master node, but your replica is in different data center. Same with Kafka, for example. You have 2-3 brokers which replicate the same topic. When you lose one broker, 2 other brokers will still continue to work, etc., etc. On the lower level, again, the data is replicated for S3, for example. And if you lose the data in one data center, you have it in another. One important thing, always have your backups somewhere else, not in your main, ideally not even in your main cloud provider or whatever you have. So have it physically in the different place, in the different location, ideally in the different cloud provider or like any backup provider. Next, we have multi-region. So for some cases, multi-zone is not enough by many reasons. The main reason usually is the geography. So you may have like YouTube, for example. It has users in very like across the globe, I guess, almost. Maybe, I don't know if it's available in China, but like mostly it's globally available. And you don't want your users to really wait long before the media comes from US to Singapore, for example. And that's why you have local replicas of your whole stack in many regions across the world. And then there is a question how to distribute the load between them. And there we have global routing, which includes GSLB, Global Service Load Balancer. How it works? It's based on two technologies. First is Anycast, IP-level technology, which gives you the nearest node, the nearest host to you, whatever you are, from the number of hosts which are within this GSLB. So for example, you have region in Asia, you have region in US, and you have region in Europe. And if you ping it, if you request the DNS entry from, I don't know, from here, for example, it will automatically go to, using Anycast protocol to European cluster. And then there is GeoDNS underneath, which understands the current, like its active load balancer, which understands the current state of your backends, of your services, the load, where to route requests, etc., etc. So it may be very complicated. And it, in turn, returns the DNS entry with the IP address of the backend, which should be addressed. And this is how it works. So you can be very flexible with setting up your global availability while working in multi-regions. Because, of course, you know, before the request enters the data center, you have to somehow, decide where actually should it go, like to Asia or to US or to Europe. This is how. And then you have multi-cloud. This gets more popular in the last time because more enterprises mostly want to also prevent downtimes or unavailability of the whole cloud providers. We have seen the recent outage of AWS, but it mostly was within one region, which again can be handled with multi-region. But you may have issues with the whole provider. Google, I guess, last year had such an outage. Something else, it's almost always BGP. But there are situations when the whole cloud provider is inaccessible, and there may be other situations. It may be some kind of network issues, DNS issues, geopolitics, sanctions, etc., etc. And you would like to avoid that. How to do that? By having your payload distributed across at least two cloud providers. And it, again, can be done in two different ways. One way is to disaster recovery side. So you have your own infrastructure with everything, and you have your DR copy of your whole infrastructure in another cloud provider and kind of network switch between them. The second copy can be cold, warm, or hot. Is it always standby and has the data, or it's turned off but has the data replicated and you have to turn it on, and it will take some time. It depends on how fast you want this second replica to start working, but you can, make this so if your main infrastructure fails completely, you just switch to the second one. This is pretty costly thing to do. Second option is that you can simply make the network using VPN, using IPsec between those two. So all of the nodes will be within the same network, and then you can within this network distribute those loads that way that you can sacrifice the half of your infrastructure one way or another. But yep, this is what it is, and it's getting more popular. So also a very nice skill to learn, and there are also very many solutions how to actually do that. Like, for example, how to build management layer on top of multiple Kubernetes systems, where we have Istio, for example, where we have Atlas, I guess. I don't remember the Google service for multi-cloud Kubernetes clusters, but there are many such as layers, meta layers on top of one cloud provider. And the one more thing I just want to briefly mention is the failover and recovery. So even if you go through all of those levels and build very, very robust application which can survive complete destruction of one data center and any kind of outages, you still cannot prevent yourself from unknown unknowns. Yeah, something may happen. Like again, if you read the postmortem of AWS outage, the issue was that they designed everything correct, everything was right. But under the load, some applications were a little bit too loaded to pull the latest changes. So their network configuration inconsistency was introduced into the system, which can be fixed, of course, but you really cannot prepare your system for every situation like this. So you have to be prepared that your system will go down completely. And you have to have, the plan B, which is called a failover. I will give you an example. There is a company, it's called Yandex.Go or Yango in some countries, and their main business is taxi, like Uber. And in their architecture talk, they shared that there is, like in their ride application, when you book the ride, there is one functionality you want as a customer never be left without. It is where you see your driver coming. And you never want to be in the situation when you update the app or maybe exiting, closing it, opening again to refresh like where your driver is. Especially when you're like in the new country, at the airport, etc., when the connection is not stable or you don't have a connection there and you connected to Wi-Fi, etc. So what they did, even if the whole system, which is pretty stable and based on, I don't know, tens or maybe hundreds of microservices, if everything goes down, they have a specific service which is extremely robust and works in isolation of all of others, which serves kind of as a failover server for the driver location information. So if the whole infrastructure of the taxi service goes down, they still have this one service which your application can connect to and retrieve the driver location information, so you will see it in your application, even if like everything else crashed completely. And this is how failover works. So identify your core functionality and try to provide higher availability for that. And also train and prepare how you will recover, how your system will recover after the outage. Because very often things like the cascade outage happens when some part of your system goes down, which creates higher load than the rest of your system can handle. The other parts of the system goes down, and this creates such a wave of a crash, which goes from one side of your system to another. I've seen that in life. That's not the experience that you want to. So also care about how the system will recover, how the load will be redistributed across the system, and also how the system can gracefully go down. So not everything is down, but you sacrifice part of your load to give your system time to recover. And the last thing in this pyramid, which actually kind of wraps everything around, is the support and maintenance. So, and this is the last, I guess, pillar of the highly reliable infrastructure, highly reliable architecture is CI/CD and supply chain. So about CI/CD, you have to have repeatable builds. So if you build the commit, it should always produce the same result, which means that dependencies are versioned and they're everything what you need is there, and the result will be always the same. Otherwise, you may be in the situation when you need to rebuild something to deploy it very, very quick because your production crashed, but you're unable to. Second, deployment should be, of course, automated. Maybe that's something I don't have to mention in 2025, but there are still companies where deployment is at least semi-manual, and there is a human involved. And just don't do that. Avoid it completely. We have enough tools to completely automate it. Autonomous rollbacks, which is more important that when something goes wrong, the system should be able to roll back automatically, again, without human involved. And that's pretty easy to achieve, actually. You can use patterns like blue-green deployment or canary deployment, so see how your applications, newer version of the applications behave. If something is wrong, it automatically undeploys and redeploys the previous version. Or with blue-green, it just switches traffic back to the previous version, which is still there and live. And also the databases should support this kind of stuff. How to do that? So you want to prevent the situation when you roll out applications and simultaneously update the database schema so that you can no longer use your previous version. Because with automated rollback, this old version of applications will just stop working and you will crash your system completely. You always have to have your database schema supporting two latest versions of the application. So the current version and the previous one. And so that if you want to roll out some break-in changes in the database schema, you have to do that in several steps. So you first roll out the kind of intermediate version of the application, which supports the new version of the schema and the old one, and the schema supports both. If everything okay, you roll out new version of like second version of the application with complete changes, and again you gracefully remove the old version, and only then you can kind of live with that. So you have also two database migrations in that case. Next, dependency vendoring. You have to have all of your dependencies locally. Basically, your whole supply chain, not only code, but also container images, etc., applications that run in your containers. You have to have it can be in repositories, it can be in registry like Harbor, for example, but you should be able to continue working without the internet, for example, when you can no longer pull this from Docker Hub or from somewhere else. That's also very important because when you will have, the Node developers, I think, knows the best, the supply chain issues. So this is the way to prevent it. And it's very important for higher availability because when everything will go bad, your builds will also no longer run. And then you have to monitor constantly the security and vulnerability of, again, everything you download from the internet, container images, libraries, etc. There are tools to do that. Yeah, you don't have to do that manually. And the infrastructure you use should be automated, ideally with infrastructure as code. So it's either Terraform, Crossplane, Bicep, Ansible, whatever, but it should be in the repository where you can actually check what is there, when you can replicate the same into different stages, and also you can build a proper review process when you change something. And most important, you can roll back to the previous version if you completely break your infrastructure, which can, happen in the cloud environment pretty often. And you have to actually teach your team what to do in case of disaster. And you have to do that before you have a disaster, right? So, because, when people are panicking, their logic thinking just doesn't work anymore. So do this before. And another way to do that is chaos engineering. A little bit different, but still this is introduced by Netflix, I guess. The idea is that you always have something broken in your productive system. And your system should survive this. And you constantly introduce new problems with API, with connection, with everything, the whole infrastructure stack. Where you actually, when everything goes well, you check what will happened if something goes wrong, so that when something really goes wrong, you're already prepared. And again, there are tools for that, Chaos Monkey, for example. And you have to, if you're building real application, not the pet product, you have to care about support, and you have to define which team and has responsibility to what, and how you have to have some system to actually create support tickets and work on them. It cannot just be pen and paper. And you have to have an escalation workflow so that first the call or the email or something goes to L1 support, where people are lower qualified and work just with scripts and knowledge base. Then if they cannot do that, they escalate to L2 support with more qualified engineers. And if they cannot do that, they escalate it to developers, L3 support. And yes, you have to have these scripts and knowledge defined. So you have to define actually step by step what to do if something is broken and like your angry customer is on call. And you have to have, of course, working monitoring system which will give you a fast access to root cause analysis. One good, that's not an ad, but one good way to do that is to use something like a Dynatrace, Austrian company, which provides this kind of holistic root cause analysis, which by collecting all the metrics, traces, and logs from your system and then trying to analyze them together to quickly give you the response. What's important here is that the time, how much you can react and fix your system. And you have to set up on-call rotations. So for L2, L3, there will be real engineers working there, not just some call center, no one knows where, which will get calls when they're at home, when they are on holidays, and you should build this process and discuss this with your people. And this is the whole picture. But are we missing something? I guess we are. So the money. The thing is, building such a system may be really, really expensive. And you have to ask yourself, will this really generate so much money for my company as I will spend? Because the spend will rise exponentially as you move closer to 100%. So it's mathematically not possible to achieve 100% availability, just know it. It's not mathematically possible, but you can achieve 4 nines, 5 nines, but it will be like exponentially more expensive. So ask yourself, do I really need that? In some cases, like a taxi service, the answer is yes, absolutely. If you run an online shop, for part of the system maybe. So for making an order, yes, probably. For payments, delivery, it can wait a bit, right? And also the question is build versus buy. But in this context, it's more about or own versus rent. So do I really want to own the whole pyramid, or I want to rent part of it and delegate the complexity to third party? The answer is it depends on your size, and like if you're a big telecom provider, like Deutsche Telekom, for example, you want to own the whole thing. If you're a small software as a service company, you probably want to delegate as much as possible to make your roadmap more flexible. Because if you will build something, this is not just very expensive, it's very long. You have to build the team, you have to learn the hard way how to support this. And I did this while working in a cloud provider. We learned very, very hard way because when you start working in a cloud provider, there is almost no open information about how to build one. AWS does not goes and shares how they did it. They share a lot of information, but not the tiny bits. And this information is unique. Not so many companies in the world own the information how to fine-tune Kubernetes, for example, for multi-tenancy. Yeah, how to run multiple payloads on it, etc. So it is very important decision. Maybe you are, Elon Musk or DHH who want to really go crazy and have everything under their own control. This is kind of one of the ways, but you have to just understand how much it will cost in money and time. And so, summarizing the talk, how we reach the 4 nines. First of all, this pyramid. You can make a photo of it if you want. So understand, even if you are not working with all of that, and probably no one really works except for really huge companies works with data centers, for example, or owns their data centers, you still have to understand what's there. And if you need, as closer you will go to the 100% of availability, as you know, deeper you go, so deeper you go into this stack. And yes, just keep in mind what you have when you're working with software. And also, if you're as a product owner, don't really want to spend your time to the rest, just rent it from public cloud, from private cloud, like, I don't know, Azure Stack, VMware, etc., and delegate this complexity to them. And next, yeah, those pillars of higher availability that we discussed: redundancy, load management, data replication, fault tolerance, self-healing, disaster tolerance, failover and recovery, and CI/CD and supply chain. So basically, we want to eliminate single point of failure. We want to distribute load evenly. We want system to understand its state and actively trying to get back to homeostasis from any situation it is in. The one way to do that is infrastructure as code, like in Kubernetes, for example. Kubernetes actively tries to get your infrastructure to the desired state, which is described in manifests. And think about location, where your payload actually is, and also try to prevent, losing everything when one data center just burns down. And keep people educated, keep people trained, and keep your supply chain secure. That's all. Thank you so much. Questions?